Sir?
Hello, yeah, you can hear me?
Yes, Professor. So let's get started, Professor.
Sorry.
Recording in progress.
Okay. Okay, so yeah, I think you can see the change of slide also, right?
Yes, sir.
Professor. Yeah.
And
Yes.
audio is also clear. Okay.
Yeah.
Okay. So welcome you all for the second day of my lectures on quantum computing. So I will try to give a big picture of building quantum computers using photonic systems. So you might have heard from other lectures also that there are different hardwares which has been explored to build quantum computers. So all that is needed as a resource is some quantum systems in which you can have control over the degrees of freedom, and wherever whatever is found as useful resources, people have been exploring the opportunity to use them as qubits. So over last few decades, photonic, superconducting qubits, cold atoms, ions, NMR systems have been explored to a very reasonable level, and people do see a very promising candidates in them. So among all of these hardware, superconducting, photonics, and ions are uh, considered to be very good candidates to implement gate-based quantum computation. So I'll try to give some overview of how photons can be used to build quantum computers. So even before people consider to see whether there's a feasible candidate or not, there has been DiVincenzo's criteria. Professor DiVincenzo came up with a set of criteria where he said, if you want to consider anything to be useful to build quantum computers, then they should fulfill certain criteria. So one is a well-defined state space for qubits. So when we say well-defined state space, which means that I need to be able to define clearly that there are two possible states which are which you can realize on that particular system. So it's like, when we say 0 and 1 or 2 states, so you should be able to define them very clearly in any hardware or any system you are going to take. And that's the first criteria. And then ability to initialize states of a qubits. So it's not just doing some quantum mechanics experiments, it's to do computation, which means that we need to be able to initialize qubits. I need to, what now, if I'm writing a program, I need to say initialize my state so and so, and then you start doing operation. So qubit has to be initialized, whether to state 0 or 1, and you should be able to control them efficiently. And a long coherence time. Now, this could be a relative term, but still, the way I also described in my last talk, that the quantum systems are very fragile. They may not have enough time to remain quantum mechanical, and the noise can destroy their quantum behavior very quickly. So there should be a reasonable coherence time. When we say long decoherence time, which means that that long is defined by some sizable gate operations implementation time. So only then you can start even considering them as a serious candidate to build qubits, and ability to implement universal set of quantum gates. So yesterday I did describe about the Pauli operators, the few basic gates, single and two qubits gates, which include Adamant, Pauli and control not gates. So you should be able to implement all such kind of gates. And then a qubit specific measurement capability. So you should be able to make measurements on qubits. So that's also, I mean, if you're treating it as a computer, then at the end you need to make measurement and interpret. If you can't make a measurement, then you'll not be able to see them as a suitable candidate. So these are five basic criteria. In fact, there are a couple of them which has been added later on, but we'll stick to the five elementary criteria which was defined. Now let's see with photons, right? So I'll say if I had to take photons, so I'm not giving a detailed introduction of photons, but photons are a fundamental particle of light, right? So laser light would have millions of photons. The light around us would have, would be, what we have been bombarded are photons of, different frequencies, and that's what makes it white. So they're all bombarded from all directions. But when we are talking about photons for quantum computing, we are talking about one photon, a single photon. It means that one after the other, we should be able to have photons. So they should be individually manipulable. So will that fulfill all these criteria? So let's say I can even take a simple definition for photons and then say a photon is traveling in one particular path, and the presence or absence of photon itself can be treated as 0 or 1, right? So all that I would need is I need to map something so that I can realize qubit out of it. So there is multiple ways, but one of the simple ways would be a single rail encoding is what we call, which means that there can be a path for a photon to go. Photon presence or absence can be treated as state 0 or 1. There is also dual rail encoding, which we call like our railway tracks. You have two paths. The photon is in one path or another path, or it can be in superposition. So which means that if the photon is in one path, we definitely know it's not there in another path. And that's what we call as a dual rail encoding. Now this helps us to satisfy the first criteria. Now ability of initializing the qubit states. You can initialize them. So now whether I can decide where my photon has to go, whether photon should be there or not, and even if I have multiple photons and many paths for it to go, I can still define, I know whether the photon is going in one path or other path. So I can easily initialize a qubit state I want. I'm just giving you a simple definition of paths, but later on we'll also introduce polarization, how you can even treat polarization as a qubit, but this is simple. Like long coherence time, or what we call decoherence time needed is very long. But photons are a very good candidate for that because light doesn't easily interact with the environment. So they are, they are very, very robust. And because of that, you can actually consider them to have a very good decoherence time. The long decoherence time is for photons. So that helps you to implement some set of gates with that. Now, ability to implement a universal set of quantum gates. So there are various ways you can implement gates, but now if I say I take two paths for a photon to go, and I can use beam splitters to change the path. I can use wave plates to change their polarization state, or I can use phase shifter to give some phase to the photons. So in that way, I can use some of those optical components to implement universal set of quantum gates. So in that way, you can see the first four of the criteria can be easily met by photons, and one can also measure them effectively. So it means that I can detect photons. Now I can detect photons different state also, whether photon is coming in path A or path B. Depending on that, I can say my measurement was state 0 or state 1. So you can effectively make a measurement on a photonic system. So photons was considered as one of the earlier very promising candidate to build quantum computers, because by that time, early 2000s or late 1990s, also people had demonstrated or played around with photons in laboratories. So in that way, it was a very, very promising candidate in the beginning. But I will also highlight, it's not always about positive things, right? Like the advantages are something which I told. The quantum operations can be done at room temperature. They are robust against external environment. As I said, they don't interact with the environment. So it's not true with any other system, any other qubits we consider. So they are very, very fragile to the external environment. If I'm taking a spin, even if there is some magnetic field nearby, the spin gets altered, electron spin. So if I'm taking superconducting qubits, even a small temperature variations or surrounding would actually decoher the quantum states, the qubits very quickly. So that's something which does not happen with photons. So they're very robust. So access to multiple degrees of freedom, and that's something very, very interesting about photons, and none of the other hardwares provide them. For example, I mentioned earlier in my previous slide that you can decide photon is in path A or path B. That is one way of defining qubit. The other ways I can even take polarization. I know light has polarization. So I have horizontal or vertical polarization. So which means that if the photon is in H polarization, which is horizontal, I can consider as state zero. V polarization can be considered as V. Now, a circular polarization is a superposition of H and V. So I can even imagine that how easily I can, or we can actually realize superposition also very efficiently using polarization degree. Similarly, one can change frequencies of photons, and that's also is considered as one of the important useful degrees of freedom. So you can encode qubit in many ways using photons, and that's another important. Most of the hardware and the fabrication techniques are very common between classical and quantum optics device. Like optics has been a very thriving subject for over century now. So now, because there has been a lot of development over optical components, we can actually use the same thing. What would be different is instead of using common light, standard light, you need to use single photons. Then when you are using single photons or a quantum state of light, then the components has to be a bit more precise, very highly engineered. But the rest of them can all be done by just using a standard optical component. So these are advantages. So one might ask, so when we have so much of advantages, then why have we not built large scale quantum computers using photons? So why we still lack that opportunity? Just simply because there's a much more, all of them, the greens are the most positive things, but there's a one big challenge. In fact, I told in my earlier slide and also in my second point here that they're robust against the environment, which means photons don't interact with the environment. That is very good, but the same thing affects that within the operations, which means that photons can't interact with itself, which means that you can't do two qubit gate operations easily. That means you are in a big roadblock. If you can't efficiently implement two qubit gates because they don't interact with themselves, along with not interacting with the environment, doing a two qubit gate operations becomes a very big challenge. And other challenges being that photons move very fast, 3 into 10 to the power 8 meters per second, because they're traveling very fast. We won't be. I know we need to come up with some ways to do quantum gate operations very quickly on them, right? So I can't continuously keep changing whatever, if I had to dynamically change the operations, photons would have already gone, right, from one point to other. So I need to engineer or I need to design my circuits on operations before the photons are passed through, and that's another challenge. So these two challenges has been there for photonics. Similarly, for all other hardwares, we can come up with some advantages like this and challenges. So people try to work around these challenges and find some solutions, and that's what something which I will try to convince that there are different ways that people are trying to address these challenges, and we do see them coming in my future slides, right? So there are different models. Again, I say, because I said you can encode them in many ways, you can also start thinking of how I can encode and how I can control what are the degrees of freedom you have, right? Even computation itself, I think in the last talk yesterday, I also mentioned about universal quantum computation and special purpose quantum computation. Universal quantum computation does not care about what kind of problems you are looking at. You can give a problem, you can always take those unitary operators, convert them into gate operations, implement the circuit. And that is one way which we call as a discrete variable quantum computing using photons, single photons. As I mentioned, you can have dual rail or polarization or which path, which frequency, time bin, which means a single photon can be in superposition of two times, and that's possible. And you can also take higher dimensional photons or like different degrees, and you can treat them as qubits combined together. So there is various ways you can encode qubits and you can do operations. So there you can see in the slide here, this is an example of a dual rail encoding. Now I can take a single qubit with 1 and 2 to be the path for a photon, and there is a qubit 2, there's again 3 and 4. I can add 2 photons, right? This is one photon and the other photon. Now if I had to do gate operations between them, then this is a bit difficult. As I said, because they don't interact, we need to come up with some unique way to make them forcefully interact and do my 2 qubit gate operations, because that's what makes it complete to do a quantum computation. And I will address that later on. NS gate operations, I'll say what that means. So that's something which the model was developed long back by Neil Laflamme and Milborn. It's called KLM model. And they came up with some solution to see how you can overcome the 2 qubit bit operations. But of course, that was not deterministic, it's probabilistic, which means the success of implementing this NS operation is low, but you can implement. So which means that every time I need to implement this operation and make sure that has been done, only then you can go with next operations, or your computation task will fail. But it is still considered a good step forward, because there is you saw that there is various other green kind of features, right? Which means that positive things about photonics. So even if it is probabilistic, it was considered as a reasonably good one. So what this NS gate operations, as a nonlinear sign change is what we call, or the sign change operation, would do that it itself involves that you need to bring in one more photon and make it interact with these photons to make the first and the second photon interact. So it means that to make 2 photons interact, I need to bring in a third photon into the path and then introduce this gate operation. So this whole of this NS would come and fit in here, right? So the input state, this was considered as an input state, which is I here, and then this is one more qubit which comes, and then you have a beam splitters, which kind of, depending on whether I measure 0 or 1, I can say that my gate operation has been implemented successfully. So by looking at this measurement, I can say, okay, my gate operation is not success, let me discard. So that's how they do this probabilistically, and it is good, right? It's still very promising and people are implementing. There is another version for quantum computing using photons. We call them as continuous variable approach. Here, you don't need a single photons, but you can take a unique way of configuring light. It's called Gaussian state of light, where you can squeeze them in different orientations and then treat that squeezing as zeros and ones. Now, by using various optical component, the squeezing parameters can be controlled, and you can implement gate operations. So we call them as Gottesman and Pitowski states, GKP states, and the operations on them would be Gaussian state operation, just like this here. So you have a coherent state of light. Laser light is always considered, a good laser light is coherent, but if you squeeze them, you will get a orientation in X, or you can get them squeezed in Y. And now that itself can be treated as 0 and 1, and you can control them. And depending on how you measure, you can say whether the output is 0 or 1. So now you can have the squeeze states in an array, and then you can create a multi-qubit equivalent, states using photons. So that's another promising CV approach. In photonic quantum computing, we have these 2 big, very prominent approaches, discrete variable and continuous variable approaches. However, to overcome this 2-photon interaction problem, there's another standard proposal which came, and then people have again tried to implement them in various ways. It's called a measurement-based or a one-way quantum computation. So what it defines is that, I can add this example here, where instead of taking photon by photon and bring them together and do a gate operation, by some means, if I can create a multi-qubit entangled state, which means that I can take there's some 2-dimensional lattice like here, where I can make them in a maximally entangled state of all the photons together. There are some ways which one can do. Then I can start making measurements on particular positions, and that can be made, or one can show that there is some equivalence of that with the gate operations. And the final output you're going to measure after making some sequence of measurements at each lattices will be your final result. So that's called as measurement based or one-way quantum computation. It's considered one-way is because once you start making measurement, you cannot reversible. So you can, because measurement always destroys the unit chances of doing some unitary operations. So that's still called a cluster state quantum computation. People, and now, as you said, there are advantages and disadvantages of all even these approaches. Though I'm not going into detail, but this is probabilistic discrete variable. And here, in a continuous variable, measuring them has not been very easy because the shape can slightly get distorted when it's passed through various optical components. And even though if it is pure, it might end up looking like squeezed, and the squeezed parameter, can actually get deviated bit, and then you will not be able to easily measure them. So there are difficulties. So people also have come up with proposals to come out, have tried an hybrid approach of CV, DV, and cluster approach in higher dimension state. It's also called fusion-based quantum computation. They've been exploring. And on top of all of those things, there is always a very unique special features, right? I told in the beginning that photons have a problem of not being able to interact the way we want, but they have their own way of interacting. It's a bosonic. Photons are considered as bosons, or they are bosons. So bosonic behavior has some unique characteristics. Now that can be easily implemented, right? There is some one specific way to photons behave, and if you can exploit that, then that itself can solve a very important problem, which no other hardwares like superconducting qubits or ion trap systems will find it very, very difficult to solve, and that's called as boson sampling. I tried to give one more. I think yesterday also I briefly mentioned about it, but that's one special purpose quantum computation one can realize using photons, where you don't need to implement gate operations, but just exploit the bosonic behavior, like how two photons interact in their unique way. Then you start making two photons, three photons, five photons interact, and that becomes a very complicated problem to simulate in a classical computer. But the quantum computer or whatever the bosons or the photons, when you just make them pass through, it will easily simulate. So all these schemes have been realized for realizing the universe has been experimentally verified at a very small scale. So that says kind of us, right? So this is the way one can define qubits and operations on them. So I can take in a discrete variable approach, qubit could be like H and V, horizontal and vertical polarization, as it is in this slide. I can now change the polarization to right circular, left circular, diagonal plus, diagonal minus sign, and there's either Poincare sphere or block sphere representation, what we call. Now, by changing the polarization orientation, I can make any uh, unitary single qubit gate operations on photons. So the optical components you would need is what we call as half-wave plates or a quarter-wave plates. Half-wave plates changes the phase by pi by 2, and quarter-wave plates change by pi by 4, which means that you're getting that phase and then you're making it circular, left circular, whatever, whichever point you want on a block sphere, you can actually go. There is a unique gadget or a combination of quarter-wave plates and half-wave plate, which people also have developed, where you can go from any point on block sphere to other point and implement any single qubit gate operation. So projective measurements is very simple here. Like if I take a polarizing beam splitter, which means horizontal polarizations transmits, vertical polarization reflects. So whatever state of light I'm going to take, whether it is H plus, H plus V or with some different probabilities, that gets distributed over here. This will be, if I check alpha H plus beta V, then the probability of getting alpha, H will be modulus alpha square, and probability of getting V will be modulus beta square here. So I can make a projective measurement onto the states using a PBS. So now this is just a simple optical component, which is present in almost all optics lab. All that you would need is a single photon in which you can control, and you can start implementing those gate operations, right? So in a similar way, there are ways which people have been using uh, continuous variables, as I said, squeeze states. So I can take squeezing in x direction, squeezing in y direction. We call x and y parity, and even them, like for example, if you're seeing here how your ex and ey, right? So you have ex and then ey, and they represent equivalent to what qubits are here, like horizontal polarization, vertical polarization, if it in state ex, and if it is ordinary in y, or 0x ordinary is just equivalent to vertical polarization. So this is a squeezing variation, like squeezing picture, and their equivalent qubit representation are shown in the sphere which are here. So in that way, how I can change my shape, my orientation from x to y to x, those there are face plates which do those jobs, and then there are also optical components. Just by having this internal reflections in various x and y direction, your x orientation could have become y orientation, and people have been doing these things very efficiently. You can also make projective measurement, right, by seeing whether my x or y, this orientation or ordinary or extraordinary ray can be separated spatially, and then you can measure them very efficiently in a continuous variable system. The only issue, as I mentioned earlier, was if these optical components, because these are beam shape, these optical components can distort the beam shape because of many internal reflections. You might end up, being unsuccessful or a deviation from a standard expected value. So these are the two standard ways one can define or encode qubits into photonic systems. So now if I just take a simple example of an operational example for polarization qubit, we can see H and V polarization. Now, if it's H or V, it's a half-wave plate, right? A lambda by 2 plates, which I said here there is an half-wave plate. If I use an half-wave plate and rotate, if it is H, then I would get H plus V, that's circular polarized. If it's V, I get H minus V. Now this is not almost, this is actually an Adamant gate operation, right? So which means that just by using an half-wave plate in the path of a photon, I will end up getting a superposition state output. Now here is a simple example of how I can actually do gate operations on them, right? A simple, like I begin with any arbitrary alpha plus V state, I get a polarizing beam splitter, which means that alpha H goes here, beta V goes here, and then I can have a wave plate which can be rotated in some particular angle. So then this will be, beta 1. I can label them as alpha 0 and beta 1. And if I again do a rotation, now both of them end up having a same polarization state, and they're going to interfere, and I will end up getting some output, right? So now this is just the way you can actually do operations, and you can measure them approximately. All that's saying is that you can begin with single qubit state, you can manipulate their states, which is almost like doing some task, some operations, which we can say it as a zeroth order of computing, right? Some change of states, and you get a measurement. So I mentioned what is the limitations of photons for 2-qubit interacting. The previous slides, this only talks about operations on single qubits, right? Which we can say can be efficiently done. There's no question about it. Now 2-qubit limitations, right? This slide captures everything to do with the 2-qubits limitation, right? So I'll begin with the simple A, where a beam splitter, right? Beam splitter is can be defined as an input and output mode. If there is a light which is propagating through A1, one of the modes, the output would be B2 plus B2 and A2. This is the output modes. If there's an input from B1, again, it will be in superposition of B2 and A2, a single photon. It's a similar way. These are not ordinary beam splitter, but similarly, we also have polarizing beam splitter, as I mentioned in my previous slide, where depending on the polarization, it will take different paths, right? If it's H and V which is coming from here, H will go here, V will go here. If it is H and V coming this way, horizontal will transmit and vertical will get reflected. Now, what happens is that I can actually use wave plates, change, and I can always get them going to any path in a single one. Now, this D is something which captures what happens if I have to do 2-qubit operations. Then I need to take 2 photons simultaneously, A1 and one more photon to B1, and then I need to make them interact at somewhere here inside the beam splitter, right? So that means that I should be able to do some operations, 2-qubit gate. What ideally we should expect is that 2 photons, possibilities, right? Both the photons come out in the path B2, or both the photons can end up being in path A1, like output mode A1. And ideally, the other possibility is that one photon takes B2 and other one takes A2. But bosonic behavior of photons forbids. You might recall that, Fermi and bosons, bosons try to occupy the same state when we are in our elementary physics classes we have studied. So that's what happens here, right? Because two photons, the moment they interact, they will end up going together. It's at the boson or photon bunching problem, right? So it means that they bunch together and they take same path. So only the first and the second one in the DUI will be possible, and the third one does not happen at all. Now that is what we mentioned about limitation of two photon interaction. Only if I have all the possibilities extractable, then I can effectively do gate operations on them. But that does not happen here with photons. And that limitation is what we're talking about. Bosonic behavior limits photon-photon interactions. Only specific outputs can be obtained, but not a generic output with that two photon. So to address this problem, so they came up with nonlinear phase shift approach where you can, the moment you are trying to introduce some phases, which means that when the moment there is a phase introduced, then they can end up seeing that as two different photons which are not identical or something, they don't interfere and they end up going into two paths. That's a very crude way of putting the problem, but this is a nonlinear sign phase shifter operator, which you call sign change operator. Phase shifter, if I give some input state, when I do this, there is going to output, and that would say it's giving you a nonlinear sign change or a phase shift into an input state. The moment you can give a different phase to an input state, then they will not see them as identical photons and they don't interact, and the possibility of them going, don't interact like in a bosonic way, but they can take two paths separately, and that can be realized using it. But there is a success probability which is actually lower than 25%, which people are trying to look at. So this is a standard way, and any table when you look at an optics experiments where photonic qubits are realized in a bigger picture looks like this. And you can this BBOs, what we see here, these are the two possible two um, setups, or a setup which is generating single photons. So single photon generation itself is not a trivial task. It's been quite hard for people have spent a lot of time to come up with some ways to generate, and even now people are looking at multiple ways to generate single photons efficiently. But one of the standard approach, what we call a parametric down conversion, I'll also explain that in later slide. So right now you can think that this is a setup where you are generating single photons, and then you can see here there are some plates here which you call them as QHQ plates, or like you can control the polarization of the photons which is entering here. Now photons can be sent to this path, and then like in my earlier one of the earlier slide, I said you can define a path for a photon, you can make them interfere. So this is some way of changing their polarization degrees, make them interfere, and then you get them to our detectors, and that would be your outputs. So using a combinations of optical components, you can implement some computation on a photonic system at this point. A scaled up portion where this is a what we call an optical waveguide schematic representation, where people have been designing and trying to develop a large scale photonic quantum computer, where you can see you can bring in a coherent pump splitting fault, but you can ignore all of those things. But this is mechanism which has been developed to generate photons, single photons. Now from this point, you will have a single photon generated. Now there are multi-photons which will have dual rail encoding or a kind of equivalent to that. So now you can make them interact, control them, and split them around, make them go in multiple paths. So these are all routing, doing some of separation of photons to go in some particular path. And then you can do qubit gate operations just by making them interact with some unique ways, and analyze, you can measure them, and you can look at it. So as I mentioned in the earlier slides, where you need to have some reference, and this are like idler, the computation happens here, and the idler is kind of reference point, because we want to know whether my computation has been successfully performed or not. But this is one of the examples of the 16 qubit system which was demonstrated. And this is a example which I think I showed this slide yesterday, and again trying to repeat, because I showed this bosonic behavior, right? So which means that's when I make two photons come together into a beam splitter, they only take a defined part, like both the photons will go together. Now, when two photons are come together, and if a third photon comes into another beam splitter, then there will be some probability, or not probability, there's three photons will take simultaneously the same path. So in that way, now if I have multiple photons, multiple photons entering, and many beam splitter in that path, then every time at every point you're going to have some
Professor, sorry to interrupt.
yes, yeah, please.
The voice is bit low.
Oh,
Many
okay.
participants have put that.
Okay. Let me. I can just see if I can increase. Okay, sorry. I just tried to check the mic again once. Is it better now?
Better, Professor. Yeah.
Hello.
It's better, Professor. Professor, it's better. Professor, can you hear me?
Hello.
Professor, can you hear me? You're on mute.
You're audible, sir.
Can you hear us?
Is it better now? Can you hear me?
It's better,
Yes,
but
sir.
can you hear us, Professor?
Hello.
Soumya, can you hear me? Professor is not able to hear us.
Yes, sir. I am able to hear you. You're audible, sir.
But
Your voice is
Professor is not
audible.
able to hear
Now?
us. Professor, can you hear me?
Hello, Dr. Ram. You can hear me?
Yes, sir. You're audible.
Okay. Is it better now? The input voice?
Yes, sir. It's better now, sir. Thank
Better.
you.
Go ahead, sir. Go ahead. Go ahead.
Okay, sorry.
Can you hear me?
Yeah, I can hear you. Yeah, sorry.
Please go ahead. Please go ahead. Sorry.
So I will also be a bit louder. Let's see. Okay. This is a setup where you have a lot of beam splitters and many photons, and then when you make them interact, so you will see a bosonic behavior coming up at every point they interact, and the output would give you something which is uh, very hard to calculate computationally, and that's something which people have demonstrated using 76 photon. Actually it was 114 photons were used, but they could detect 76 photons in some particular pattern, which showed that no classical computers can actually simulate them and look at it. So this is a very good demonstration of a good demonstration of taking advantage of photonic behavior to do something which is very useful and important. This also addresses one of the mathematical problems which they call as calculating permanence of a matrix. We are all familiar of calculating determinants, which means that there is a diagonal element and off diagonal element. So we put a minus sign and then you can calculate determinant of a matrix. But if you put a plus sign, then that is called as a calculating permanence of a matrix, and that's considered a mathematically very hard problem. You can just go back and check with the textbooks. Now that is very much similar to bosonic behavior at every beam splitter level. So that's why they consider this as a boson sampling problem, which has some similarity with the calculating permanence, which is considered as one of the computationally hard problem, and that can be effectively solved here. So you can see here on top of there are a lot of beams or like light laser photons are going through, and there are beam splitters placed in there, and then there are a lot of waveplates which are used to control their degrees of freedom in this setup. Right? So now there is other important aspect which comes to the picture. I know single photon I can control, I can demonstrate, but if I have to do a large scale computation, then I need to entangle them and I need to use entangled photon as a resource. So there are various ways which people have been trying to work, but one of the most established methods is called a parametric down conversion. And this is a setup which people use some unique crystals to generate entangled photons, and I will define them. And there are multiple ways, as I said. This is the well-established way where you can send a laser light, make it interact with some crystal, and that crystal output from that will actually give me a single photon. And that's not just single photon, it will also help me to generate entangled photons very effectively. These are available, or one can do them in room temperature very efficiently. But the problem with that is we don't have a control on the light interacting with the crystal. That's decided randomly by nature. So which means that you don't get an on-demand single photon, which means that I can't say at time t is equal to so and so, please generate a photon. I can only say is that I have a light at some point in that time window generate. So you will get them in a nanoseconds time differences most of the time, but you will not be able to pinpoint that this can be generated at a specific time and everything. But there are other ways which people have been, and one of the most standard methods would be the quantum dot method, where you have some source and then you have you try to excite them with some particular light, and then the dots emit photons of some particular wavelengths. And this has been considered as one of the most promising ways to generate on-demand single photon source. People have been working on it, but they are not still very efficient. But that will help you to get photons the way you want. And if that successfully happens to a very high accuracy, then you can actually put these sources into a photonic integrated chip, and scaling up quantum computers using photons will not be an hard task. But there are other challenges with quantum dots. One, it's generating entangled photons is very hard, which is very easy with the down conversion method. And it's also difficult to use because directionality and few other things, and it needs a cryostat, a few kelvins now, to hold those materials which can emit photons for us. So this, and also there's other issues like they are not very pure till now, and people have been trying to generate a very highly pure source of single photons. But having said this, there are promising ways, these are promising methods to generate single photons, and people have been using. So I will describe one of the most, that is the parametric down conversion approach. What I mentioned was that there is going to be a crystal, so I can send some light of some particular wavelength, and when it goes inside a crystal, it has some interactions with them, and during interaction, now single photon of some particular energy becomes two photons of lower energy. And that happens once in a million, right? The rest of the light, nothing happens to that. If you see in the first image, there is some particular color light is passing through, and then there is two photons which come out as single and idler photon, but there is one more path, nothing happens, the same thing is going straight, right? So which means a lot of photons transfer without anything happening to them, but then there are once in a million you will see that they lose energy and become two photons of lower energy. So this is a schematic diagram of the conservation of energy, and there's also conservation of momentum. That's what we understand from our very early days physics, right? So this conservation of momentum is very important, or else you will not be able to account for how you get some particular directionality, right? So here. But a more simpler way to even describe them is that I can consider it like, or I can actually see a parallel with that with an atom, right? If I consider an atom and I shine some light into an atom, there is a lot of light which goes through, nothing happens, but there's one light which can excite an electron, one photon in that million, excite an atom from ground state to an higher energy level, like you can see in this image B. Once it goes to a higher energy level, it sees that, oh, this is not my stable state, I need to come back. When it tries to come back, it stays a metastable state, and then when it sits in the metastable state, then one photon is emitted, and then it realizes, okay, this is not my ground state, and again it ends up going to a ground state and two photons are emitted. So that's a very naive similarity between what we call as down conversion method and the lower energy photons generation which is happening right now. Because of conservation of momentum, as we see here, at any given time there might be only one pair which gets generated, because now I send one photon, Now that is becoming 2 photons at lower energy. Now I can engineer crystals and momentum, the way the momentum conservation would happen in that crystal during when they interact. So you can create certain geometry. There is one standard geometry here. You can see 2 photons are coming, but it can come in a circle in some particular orientation. Depending on which point one photon comes, the other one will be an opposite direction, right? There are 2 cones here. So one photon will take any one of the path in the first cone, other photon will take any one of the path in the second cone. But because of conservation of momentum, the path will be at some particular opposite directions in their trajectory. Now they also have studied that you can actually use crystals which gives one photon in horizontal polarization and one photon in a vertical polarization. But now what happens is, if the geometry overlaps like this, you can see here 2 points, there is a overlap. So now we don't know whether the photon is coming from the top cone or from the bottom cone. Just because of this, in our inability to distinguish them and measure them independently, we can actually see them as an entangled state, because the moment at this point I know and I make a measurement that the photon in this is H polarization at this particular intersection point, then without even measuring I can say the photon on the other intersection point would be an opposite polarization. Now that's how, if I post select, which means that I will ignore all the photons which is coming in this ring, but just select only the photons which are coming in that superposition ring, then I have generated entangled photons. Now this is one of the versions of entangled photon generation, and this is an image from a real experiment where you can see these 2 dark spots in between are tapped to generate entangled photons. So this is a schematic representations of see how I can. Now if I don't want entangled photon, then I can use a polarizing beam splitter out of this is a big a cone which looks like an enlarged, but they are usually very very small cones in the experimental setups. All that I need to do is that in the path I need to keep a polarizing beam splitter like here, which means that one ring takes one path, other ring takes one path. Now it means whenever there is a photon in one path, there is definitely a photon in other path, and now I can use this as a single photon to my computation or various other tasks as we define. So you can, from this setup, you can generate both single photons or entangled photons. It's what we are going to take as a resource is what becomes important. So there are different kinds of crystals and different configurations of polarizations one can generate. So for example, there is what we call there are long crystals which we call PPKTP crystals, BBO crystals. I'm not going into details of what those chemical compositions are, but they are kind of treated as a gratings which can create. Now in this schematic you will see that the 2 cones overlap with one another. They actually don't come as a separate cones. So which means that you can take any 2 points diametrically opposite in the cone, then you're going to end up having entangled state like this. And there are ways you can use crystals, 2 crystals in some combinations, then you would end up having an entangled state HH and VV. So you see here with one kind of crystals I'll get HV plus and minus VH, a superposition of different polarizations. And now you can add a superposition of same polarization in other kind of crystal, right? So this is, and there are the previous image I showed that you use some particular BBO crystals, you'll end up getting HV and VH state. So there are also crystals which doesn't give entanglement, but you can end up having a unique state of single photons. Both of them can be V. I can use some wave plate, rotate them, and I can make both of them HH. So these are all like standard ways which people have been efficiently generating single photons, and these are the ways we also generate in our lab at IIC. These are images from our lab from IIC. So now all that I did till now is that how you can control the photon states to do gate operations, how photons are generated. And there are challenges of making photon-photon interactions. So people have been addressing the ways to overcome this photon-photon interaction problem at every level. It can be done at minimum level, or you can try to see how I can increase the probability of successful gate operations, 2-qubit gate operations with photon-photon interactions, things. So we have also tried to explore some different ways. There has been multiple groups in the world who are trying to work in those directions. So can we use different degrees of freedom together to generate larger number of qubits, and overcome this photon-photon interaction problem? And that's the kind of question we try to pose. And we can see there are ways people have proposed a mathematical models to do computation using different degrees of freedom of quantum state, not specific to photon. This quantum walk model, which I tried, I think briefly I tried to describe yesterday as an algorithm, where you toss a coin, you go to the left and right, and a similar way, if you can control the coin degrees of freedom, then you can actually stay at same point, go to the left and right. So you can have multiple paths for photons to go to it. In the earlier, in the first slide, I was trying to say the dual rail encoding. There's two paths for photons to go, but I can have multiple paths for photons to go. When I have multiple paths for photons to go and I make them interact, then I can see whether that can be mapped to a gate operation. And that's what we try to look at it, right? So if I just don't do anything, just make them go to the left and right and same, I end up getting some probability distribution. But at every node, when the photon is passing through, if I control the way they go to the left and right, then I will be controlling their interference. I can get any pattern I want, and that's kind of considered as. Now, if you see here, this is a position space. Where is this qubit? There's only one photon. What we can do is that I can take this position space and I can map them into qubits, right? So multiple bits. So if I have some 3 position space, or say 8 position space, I can map them into 3 qubits, because 3 qubits can be written in 8 position space. Of course, it's not scalable, it's not resourcefully scalable, but let's assume that we can do that in principle. So for example, here we have 15 position space, and then I can take 4 qubits, and then I can label the qubit basis, which means that if the photon is here, then I can consider that this is the basis representation for them. So if I have access to multiple position space, I can generate a multi-qubit system. So to break it down into a smaller problem, now I can take a single photon or any degree of freedom, and let's say photon here, and I can make them, I can treat them as qubit. If I take polarization horizontal, vertical is a qubit, but that photon can also be in superposition of 2 paths. So now this also can be treated as a qubit position space. Now a tensor product of these two together becomes a 2 qubit system. And I can take some lattice, like square lattice, just like 4 point here, and I can bring this photon and make them sit in superposition of this 4 position space. Then again, I can treat that as a 2 qubit, and this photon coming in becomes a 3 qubit system. So you can now control the way photons travel in this closed lattice, and I can define some shift operator, whether depending on its polarization, whether it has to go to the right node, left node, or I can do change in the polarization degree of freedom, and I can control their path. Now one can actually show the equivalence, or use this combination of operators to implement gate operations. That's how usually it is done even in other hardware, right? If I have to think of superconducting qubits, now I need to control my currents and the sequence of pulses which would affect the states and then change or do operations on them. In a similar way, using the way how I move photons depending on their polarization degree of freedom, I can implement gate operations. If I have to implement, for example, I did this is a photon and then there is a 2 qubit, 1 qubit, totally 2 qubit system. Now, if I have to implement an Hadamard gate operation, which means that I need to move or I need to do some kind of operations of photons on both the position, and then those define the Hadamard gate operation, the first and the second qubit. So here first qubit has a different degree, second qubit has a different degree. Now this, what is so special about it? That's going to help us to do 2 qubit gate operations very easily, which is very difficult when I'm having 2 photons. So if I have a phase, I can just do a phase change on one of the paths or operations, and I will end up getting. But to do a control knot operation, which means that depending on the polarization, if it's H polarization, you can say that do nothing. If it is V polarization, you can say the photon get shifted to another position. So now I can make a measurement and I can implement easily, I can implement C0 gate and make a measurement and verify that a C0 gate is efficiently done. So similarly, even on a 3 qubit system, like the way we add this geometry of square, you can implement gate operations. Now this S operators, what I'm saying here is the one which we say here, which are shown on the right, which is very much like horizontal polarization goes to the left, or right vertical polarization goes to the left, and that's how we define them. So even very hard, the gates which are considered very hard, like control not gate in a normal computing architecture, can be efficiently implemented using such kind of internal degrees of freedom. But the issue here is really that how we are going to scale up. Though there are certain geometries or mathematical models, but it's not been very easy to physically come up with models to scale up on a physical instance in an experimental setup. Because if I have to realize 3 qubits, I need 8 position space. If I have to realize 50 qubits just like that using single photons, then I again need 10 to the power of 16 position space, which is not considered practical, because whole idea for us to do computation is that you need to make them resourcefully scalable. So that's not very practical. But at a smaller level, at least up to 3 qubit level, it's very straightforward, because 2 to the power of 2 is 4 and 2 plus 2 is also 4. So we are not eating the spatial complexity, what called space complexities. They are identical, so I can at least easily implement any 3 qubit gate operations on a system which consists of 1 photon and 4 paths. Now, if we can do that, and if we can try to build smaller modules like that and combine them together, then one can actually implement a larger number of qubit system using lesser number of photons and still resourcefully scale is what. But there are difficulties, but the model do promise that there is a possible way to scale up and implement deterministically all the gate operations at 3 qubit level. To make one 3 qubit unit interact with another one, it may not be very easy. That is okay to have probabilistic behavior in between, but at a core of every 3 qubit, we can make deterministic gate operations, right? So there are simple examples one can use, or simple practical applications of smaller number of photonic systems. So there is one example I'm giving here is a simple 2 qubit state generation. The moment I generated 2 qubit, so just like I said, I have a polarization path. You saw the square structure in my previous slide. Now, if I have to realize that experimentally, because photons don't sit and you can't control them, right? They move with time. So if they are moving with time, then I need to create something equivalent to that square lattice. Now here, that's what it says. I have 4 points here. Now these 4 points, or a 4 rail for photons to go, is treated as a point on a square lattice. 4 points on a square lattice. So now I can actually make them go to different paths when I'm doing an operation. Now this is a simple way of generating a 2 qubit state using single photons. I can send a single photon, rotate their state, create H0, V1, and again I can change their polarization degree of freedom and create H0, V0, H1, V1, right? All the 4 basis states can be realized, and you can make measurement of those basis state independently. So there are differences here. Since I can actually make one-shot measurement of the whole basis, unlike in a system where you need to make single qubit measurements. To make single qubit measurements here, we need to make the paths interfere. We don't have to worry about it. So there has been systems which there is a Cambridge Quantum Computing tried to create some single qubit state and build a random numbers out of it. Random numbers plays a very important role in most of our security or cyber security applications, statistical modeling applications, because whenever we toss a coin, we might say they are random, but if somebody can model the environment and the tossing coin efficiently, you can say whether you're going to get head or not, head or tail in our operation. So if you have all the information, you can prove or you can show which it is. So it's called, they're all considered as pseudo ways to generate random numbers, but quantum mechanical systems inherently possess quantum random behavior. Like collapse of wave packet is not defined by anything, any dynamics. It's like it's a collapse which happens instantaneously, and nobody has a control over it. So in that way, if you take this 2 qubit system here, when I'm sending a single photon, the moment it is hitting a detector, it's collapsed to one of the detectors, right? It can't collapse at 2 places, because photons can't be measured simultaneously at 2 places. It will always be at 1, but before it's measured, it's in superposition of all the paths. So measurement would give me H0, V0, H1 or V1, any single wave. It means that using a single photon, I can generate 2 bits of random information. So every time I can generate 2 bits. So in that way, in fact, we could develop a simple 2 qubit system which can generate a large number of random numbers, which can be used for OTP generation or a CAPTCHA, which we are familiar with. They're all coming or sourced from some random sources. But using quantum random numbers, you can generate them more efficiently. So this is the first one is a single qubit kind of model, but using a 2-qubit system, as using simple polarization and part degree of freedom, one can generate a practically irrelevant issue. You don't have to go for a large number of qubits for looking at some small applications, right? So here is an example of implementing gate operations, and these are all like been demonstrated recently in our lab at IIC, where you can send photons in multiple paths and then do operations on them, measure them, because quantifying is the most important thing. We can always claim many things, but you need to prove that you have successfully implemented quantum gate operations. So all the single and 2-qubit gate operations can be deterministically realized, and these are just an examples of all the basic gate operations, control NOT gate operations, and phase gate operations efficiently. And efficiency of them may not be 99, but because they are all bulk optics, which is done in a macroscopic scale, you can still achieve them all with from between 91 to 97% efficiency. Them. So when we talk about efficiency, most of the time we do tomography of quantum states, and these are like proved from the tomographical methods. So in a similar way, instead of just looking at 2-qubit systems, you can implement a 3-qubit operations with 4 parts, and this shows how you can implement. These are all like the standard circuits at the bottom. On the top is its equivalent photonic models, how photons takes different paths and how they are going to interfere to give us certain output gate operations. And we can make measurements on them and get any desired 3-qubit gate operations deterministically. And here is an image on the right, which simply gives a very modular picture of our 3-qubit architecture, which is a real 3-qubit base. It's not the gate operations, but how you can have multiple paths for photons which is entering, right? You have a single photon which enters here, and then there are multiple paths for it. So now these 4 points are the 4 nodes on the vertices, and then there's a polarization degree of freedom, it becomes 3 photons. So in between, I can keep many of these wave plates and then change their polarizations and do certain operations on the polarization degree of freedom. And so if you see even the Hilbert space structure, you can see that the path degrees are 2 qubits and the polarization is 1 qubit system. So 4-qubit system also can be, instead of taking 1 photon, you can take 2 photons, and each photon could have part degree associated with it and make a 4-qubit system, right? If I take a 4-qubit system, then I would have 2 to the power of 4 number of basis states totally. So which means the 16 basis state. In that 16 basis states, we can choose specific, because we can engineer now, right? So the moment we can engineer them, we can choose some specific configuration. Here is one particular configuration we have chosen. We chose 8 basis state and the 8 were discard. And there is some unique feature here. The addition modulo of all the values inside this each basis state is 0. So, which means that you are trying to say 0 plus 0 plus 0 plus 0. Addition modulo 2 is 0. If I am taking any other 8 basis states, then addition modulo will be 1 from that, right? Or addition modulo 2. So what we did was we consider a specific state which has addition modulo 2, and then create a 4-qubit system. As quantum circuit which was implemented to generate such state is given on the right side. So which means that just by controlling the polarization and part degree of freedom in a small optical setup, I can implement, here we can see here 4 2-qubit gate operations and 4 single qubit gate operations quite efficiently with more than 98%, 99% accuracy. And when we make a measurement on each basis state, I would end up getting some bits measured. Like this is 4, right? Every measurement will give me 4 bit. And now sequence of measurements will end up giving me a lot bit sequences, right? There is a huge sequence along with it, right? So the experimental setup would look like this. This is just a source part generating them, and this is because photons can actually travel. I would take 2 photons. There is an entangled photon because we can actually generate entangled photon, and each one is associated with path. Like C and D are part degree of freedom. A and B are polarization degree freedom of 2 photons. So now here is C and D, like C and then D. Now, because polarization and path are there is one photon inside this and there is one photon inside this. And now both the photons are measured in some unique paths. So every time I'm measuring, I'm going to get 4 basis state. Either it collapses to one or the other, in the other one also it collapses to one or the other. So that kind of gives me a 4-qubit system, and you can actually, because they can be spatially separated, we can use them as key. Right? I am not defining how we can generate public and private key here, but we can actually keep one set at one place and other can be communicated as a private public key, and it can be announced using the combination of keys. Even without knowing what was the measurement there, here they can recover the qubit which has been measured in another place and then decrypt the image. So using a simple 4-qubit system, we can demonstrate, or we have demonstrated, secured encryption and decryption of image. Right? You can do that for any information. So all that you would need is some specific controllable state generation, and photons, unlike other qubits, you can spatially separate them or move them apart, and you can use them as a demonstration. This was also published recently. Similarly, a 6-qubit system can also be built. Like if you see here, there's about 5 entangled control not gate operations or Damart gate operations. If you go to Nelson and Chuang or any standard quantum computing textbook, you would end up seeing such kind of gate operations to realize entangled state for 6-qubit. But because of our architecture, where we take polarization part degree of freedom, I can take first and I can show that this circuit is equivalent to this circuit because connectivity, right? First and the 4th qubit are entangled straight away. And now I can entangle them, each qubit in a part degree of freedom. And that's what it does. So here, the first half of this circuit is done on the top, the second half is done on the second, but before entering that modules, they are entangled. So the circuit, the textbook circuit which is of this form, can be effectively realized by gate operations of this form, which can be done in a photonic system. Now I can control the way they move around in this particular unit and generate other configuration of a 6-qubit system. And now in the image you will see this is the source part, and then you have a 3-qubit module, and to do some gate operations there are interferometers which are here on the path, and these are all like polarization rotation plates with it. A 6-qubit state, one can actually quantify them by witnessing entanglement in such kind of system, right? So similarly, a 3-qubit system, yesterday I also discussed about the teleportation protocol, where you can teleport a quantum state. If I have a 3-qubit, then the same thing can be demonstrated using this kind of setup. There is control not gate operations, unitary operations, Hadamard, and I'm not explaining the experimental setup, but what my main purpose here is to show that a 3-qubit system is needed to implement teleportation from the textbook model, and we can use internal degrees of freedom and implement them, right? So here is an experimental setup to do the operations which are there in the circuit, and you can demonstrate teleportation with very high fidelity. That's compared to so most of the time teleportation needs multiple photons, and that makes it probabilistic. Since our scheme involves different degrees of freedom and deterministic, we can get a deterministic quantum teleportation, which is usually not possible if I'm using a multi-photon setup. So using just smaller number of qubits, we just gave example of some of the results which we could demonstrate using 2, 4, 6, and 3 qubits in recent time. Similarly, we can consider scaling up our challenges. There are challenges to scale up, and we do look at methods, come up with some modules to scale up and see how we can implement larger number of gate operations and start looking towards some practical applications or much more robust quantum algorithm implementation, right? So at this point, I would like to stop this talk and take some examples of quantum algorithms. So So there is a huge scope to develop practically realizable quantum algorithms, because as I mentioned in my the talks earlier talks that there are difficulties in implementing gate operations, large number of gate operations because of system errors and various other things. So let's see what is the current status of algorithms and what have been done in the limited systems, right? In addition to what I showed, what we have done in our lab with 2, 3, 4, and 6 qubit. So there are a few other things. Right? So there are many well-known algorithms. Right? People always just talk about two things: Shor's algorithm and Grover's algorithm as famous.